So in this video, we are going to talk about the second part of the fundamental theorem of calculus. If you missed the previous video, that's where we talked about part one of the fundamental theorem of calculus, which essentially showed that the derivative and the integral are basically inverses of each other. So in integral calculus, we're probably going to utilize the part two a lot more than part one, but both are very important. And part two says, if f is some continuous function on the closed interval from a to b, then the definite integral from a to b of f of x dx is equal to capital F of b minus capital F of a, where capital F is any antiderivative of lowercase f, that is, a function such that capital F prime is equal to f. Now, that is such a huge and powerful statement, because previously, if we were integrating something like -2 to 2 of 3x minus x squared plus 2 dx. We saw this in a previous video, and the only way that we knew how to integrate that at that point in time was by using the Riemann definition of the definite integral, which required us to calculate a limit and a summation, and it's quite a long and arduous process. And so the fundamental theorem of calculus, part two, gives us a much simpler way of evaluating these definite integrals. So let's go ahead and jump into some examples. Example 3 says find the area under each curve. So for part A, we have the function or the curve y equals e to the x power, and we want to find the area between -1 and +2. So just a quick refresher, if you forgot, the graph of e to the x is an exponential function, and it looks something like that. And so what we're doing is between -1 and +2, we are trying to find the area underneath this curve. So the way that we're going to do that is we've learned that the area is equal to the definite integral from -1 to 2 of e to the x dx. And the really nice thing about the natural exponential function is that its derivative and its antiderivative are both e to the x. So this is equal to, the antiderivative of e to the x is e to the x. And previously, you might have learned that we put the constant of integration, and that is typically when we're taking the most general antiderivative. And I'll address that a little bit later, but I'm just going to write the antiderivative e to the x, and then the notation that we use is we draw a vertical bar, and I'm going to put the lower limit of integration on the bottom, so x equals -1, and then my upper limit of integration on the top of my vertical bar. And what this notation means is we're going to take our function and we're going to evaluate our upper limit of integration, which is 2, so we have e to the second power, and then we're going to subtract off the capital F of a, which in this case would be minus e to the -1 power. So this is our final answer, and this represents the area underneath the curve of e to the x from -1 to 2. And it might be helpful to have a decimal approximation for that. So this is approximately equal to 7.201. So the area underneath this curve is about 7.201. So sometimes I get the question from students, why don't we include the constant of integration? And you actually could, because if you look back at the theorem, it says any antiderivative. It's just that what's going to happen is I'm going to put brackets to indicate that we are evaluating that entire function there with the limits of integration from x equals -1 to x equals 2. So notice that I put my constant of integration here, so I have plus c. And now what's going to happen is if I evaluate this, I'm going to plug in my upper limit of integration, so it'd be e squared plus c. and we have that, and then we're subtracting off if we evaluate our lower limit of integration into the bracketed expression. So I'd have e to the negative 1 plus c. And if I distribute this negative sign, what's going to happen is the constants are going to cancel out. And once again, we'll just be left with e squared minus e to the negative 1 power. So it's still our final answer, even if we decided to include the constant of integration. So ultimately, not including the constant of integration just makes our life a little bit easier. And that's how we'll proceed moving forward. All right, so for part B, we want to find the area under the sine graph between x equals 0 and x equals pi over 2. As a quick refresher, the sine graph looks like it starts at the origin and then it looks something like that. We know that this x value is pi. We know that this is pi over 2. So I am trying to find the area underneath the curve between x equals 0 and x equals pi over 2. And that area is equal to the definite integral from 0 to pi over 2 of sine of x dx. It's really important that we put the differential, so don't forget putting that because that tells us which variable to integrate with respect to. And this is equal to, based off the fundamental theorem of calculus, part 2, we should know previously that the antiderivative of sine of x is negative cosine of x. And we are evaluating this between x equals 0 and x equals pi over 2. So I'm going to go ahead and evaluate my upper limit of integration. So I have negative cosine of pi over 2. Then I have minus, and then negative cosine of 0. Let's see, cosine of pi over 2 is 0. So negative 0 is just 0. And then this is the same thing as plus cosine of 0, and cosine of 0 is equal to 1. So our final answer for this is 1, and it turns out that this area is 1 square unit, and that's the area underneath that curve. Example 4 says evaluate the following definite integrals, and oh look, this might look familiar because we evaluated this definite integral in a previous section, and we had to use the definition of the definite integral, which is a long and difficult process. And so let's see if we can't make this a little bit easier on ourselves. So this is for part A. We have the definite integral from negative 2 to positive 2 of the function 3x minus x squared plus 2 dx. Now, something that I want to highlight is that you want to make sure if your integrand has multiple terms that you're always either putting parentheses or brackets around it, because otherwise it's not correct. And the reason that is because we have our differential here that's essentially being multiplied to this entire thing. We're not really distributing it, but it is being multiplied to that entire quantity. So don't forget brackets or parentheses if your integrand contains multiple terms. All right, so now we want to go ahead and take the antiderivative, and on each of these terms we're using the power rule. So I'm increasing my power by 1 and then dividing by that new power, increasing by 1, dividing by that new power, and then increasing my power by 1 and dividing by that new power. And I'm once again going to put brackets because I'm evaluating this entire function from x equals negative 2 to x equals positive 2. So let's go ahead and plug in those numbers. I have 3 times 2 squared over 2 minus 2 cubed over 3 plus 2 times 2. And then I want to subtract off, and I want to plug in negative 2 now anywhere I see an x. Okay, so 2 squared is 4, 4 divided by 2 is 2, so 3 times 2 is 6, minus 8 thirds plus 4. That is also going to be 6, and then plus 8 thirds, and minus 4. And we're going to have 6 minus 6 if I distribute this negative sign, so that's going to cancel with that. And then we have positive 4 here, minus negative 4, so that's going to be 8. And then negative 8 thirds minus 8 thirds would be minus 16 thirds. And if I found a common denominator, 8 is equivalent to 24 thirds. And this would equal 8 thirds. And this was the answer that we found in the previous section when we did it using the definition of the definite integral. So it's nice that we have this shortcut to be able to solve this. All right, for part B, we have the definite integral from 1 to e of, that's the same thing as 1 over x dx. Do you remember from calculus 1 or differential calculus what the antiderivative of 1 over x is? So it is the natural log of the absolute value of x, and it's really important that we don't forget the absolute value bars. In this situation, it's actually okay if we didn't include them because we're only looking at a closed interval from 1 to e, and all of these numbers happen to be positive, but in a case where that were not true, then we would absolutely need the absolute value bars. So in this case, we could drop them because all of our x values that we're looking at are positive. So if you wanted, you can, for my class, I'd like you to make sure that you always put the absolute value bars at least in the initial step, and then later if it's justified, you can always drop them later. So I'm going to evaluate my upper limit of integration, that's the natural log of e, minus the natural log of 1. And notice that I'm not putting absolute value bars here because e and 1 are both positive numbers. So these are both numbers that you should know how to evaluate without a calculator. The natural log of e is equal to 1, and the natural log of 1 is equal to 0. So for part B, our final answer is 1. All right, let's do part C now. We have the definite integral from negative 1 to positive 1 of 1 over x to the 4th power dx. And this is equal to, it might be helpful to rewrite our integrand as x to the negative 4th power because it will be easier for us to take the antiderivative using the power rule. So what I'm going to do is I'm going to increase the power by 1 and then divide by that new power. And I don't need to put brackets or parentheses because that is a single term. So I will use my notation that we've been using with the vertical bar. And now I'm going to evaluate this, and I'm going to factor out a negative 1/3. So that's the same thing. And I could just evaluate it from x equals negative 1 to x equals positive 1 and multiply the negative 1/3 later, or just kind of factor it out. So now I have 1 to the negative 3rd power minus negative 1 to the negative 3rd power. And if you end up simplifying that, the thing inside the brackets ends up becoming positive 2. So overall, this becomes negative 2/3. Now, this should be a cause for some pause and thinking about it. Our final answer being negative is a little bit strange because if you think about the function y equals 1 over x to the 4th power, that's always going to be a positive number because if I raise our x value to the 4th power, that's always going to be a positive number if we're talking about real numbers. And so the fact that we're getting a negative value for a definite integral should be some cause for concern. And the reason that's happening is if we were to graph 1 over x to the fourth, we know that the values are always positive, and we know also that there is a vertical asymptote when x equals 0. So here's a really rough sketch of what the graph of that looks like. And we're going to learn about this more in a later section, but we can't use the fundamental theorem of calculus part 2 on this because of the fact that there is a vertical asymptote at the y-axis. So if I wanted the area, really this kind of goes off and I can't quite utilize the fundamental theorem of calculus part 1. And the reason that is if you read part 2, if you read the part 2 of the fundamental theorem of calculus, one of its requirements to use it is that the function be continuous on the closed interval that we're looking at. And as you can see, there is a discontinuity at x equals 0. So this is not continuous on the closed interval from -1 to 1. And therefore, we cannot use the fundamental theorem of calculus part 2. So we'll learn more about how to evaluate an integral like this later on in the quarter. But if you're super curious and just can't wait, this is called an improper integral. And again, we will cover this section later on in the quarter. So here's just a restatement of the fundamental theorem of calculus, including part 1 and part 2. And we're restating it just because it's such an important theorem that we use so frequently in integral calculus.